So like I was saying, the combinatorics of this pairwise selection of vertices can be mathematically understood using some simple arithmetic. We say that a tetrahedron that you see on the left side over here is consisting of 6 edges, 1, 2, inside 3, 4, 5, and 6. Sorry, this 3 is above. So this 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yeah. I missed this. 6. The number of vertices, on the other hand, are 4, and we can count to confirm. So 1, 2, 3, 4. Yeah, that is the number of vertices. The hydrogen atoms, the way we place them in this combinatorial concept of redundancy, is a pair of hydrogen atoms at each pair of vertices, and then we modify it. So we can write the number of combinations as NCR, where N is W is equal to, where the combinations are given as W, or the possibilities as N prime factorial N upon factorial R upon factorial N minus R, where the number of vertices are N, total number of vertices 4, taken 2 at a time. This is what we did, right? Substituting, we get factorial 4 upon factorial 2 times factorial 4 minus 2 is equal to 6. Just check this. So it's 4 into 3 into factorial 2 in the numerator, and in the denominator factorial 2 into, so we don't need to write that into, so 4 minus 2 is again 2, so 2 into 1. Okay, so we get rid of factorial 2 here. 4 by 2 is 2, and so we end up with 6. Okay, so our arithmetic was fine, right? What do we do with this? Now we can use this little statistical redundancy question to conceptually understand another aspect of Pauling's idea of entropy and put it in the framework of hydrophobicity. And the idea is the following. If we now have a molecule that is apolar, does not have even a weak charge, and therefore doesn't interact with H2O, then if the number of molecules are sufficient enough, let us say in one tetrahedron, such a molecule occupies one of the positions of the tetrahedron, which means that out of the 6 possible positions that the H2O molecule could take, this one, and this one are eliminated. We cannot have them, right? Which means that the possible combinations are now constrained, which means we have now 1, 2, 3 vertices, again taken 2 at a time, and we end up with W is equal to 3, right? Make sense? Okay. Entropy, on the other hand, so this was all statistics, right? Or statistics and combinatorics. Entropy, on the other hand, comes to us from thermodynamics. It's population. It's a property of a system from thermodynamics, and it also has a linkage to statistical mechanics, which we will get to in a minute. In the thermodynamic description, Gibbs free energy G is equal to the difference between the internal energy or enthalpy and the temperature multiplied by entropy, the product of temperature and entropy. On the other hand, entropy is a measure in itself of the number of ways of organizing the system. We also say that the equilibrium state of any system corresponds to the minimum free energy G of the system. That is either S is very high or H is very low. Um, the idea that S is very high is part of your second law of thermodynamics. In such a system, then the spontaneity of a reaction is determined by the change in Gibbs free energy. And again, that gives us delta H, delta G is equal to delta H minus T delta S. Delta G is negative, indicates a spontaneous reaction. Um, this was up as far as the thermodynamics goes. And now we come to a set of a simple definition which took many years to accept from statistical mechanics, which is in some sense the statistical postulate of entropy. And in its most straightforward form, coined by Ludwig Boltzmann, the pioneer of statistical mechanics. So, like I was saying, the Boltzmann's entropy law states that S is Kb into ln W, where Kb is nothing but the Boltzmann's constant. In SI units, it's 1.38 into 10 to the power minus 23 joules per Kelvin. And W is the number of ways of arranging atoms or molecules. It always begs the question, why W? What's the meaning of W? W doesn't seem to make sense. It's not probability, right? But W is a historical term in honor of Boltzmann, who was himself a German speaker from Austria. He's buried in the Vienna cemetery. W stands for Wahrscheinlichkeit, which is nothing but probability, with the colloquial meaning of thermodynamic probability. So you remember we began this segment with hydrophobicity, and we're going to sort of ask how hydrophobic effects can be put in terms of thermodynamics. And in this particular case, we spoke about the degrees of freedom. Remember that we said there are certain permitted positions for water, and an apolar molecule placed in the matrix will result in restricting the freedom of water molecules to be placed. And so we are going to describe the hydrophobic effect in terms of reducing the degrees of freedom of arranging water molecules, and therefore giving rise to hydrophobic effects through entropy. So in a sense, we'll frame this as the change in entropy, delta S, is the difference, the negative difference between the unconstrained situation minus the constrained situation. Constrained being with the hydrophobic elements in them, the molecules in the lattice. W, by definition, is factorial n divided by factorial r, and still in the denominator, n minus r factorial. This is how we had described a combination earlier. Delta S hydrophobic then becomes delta minus Kb into ln 6 by 3, 6 being the edges and 3 being the constrained edges. So let's look over here. So there are edges 1, let me just mark them, 1, 2, 3, yeah, which are permitted, and these are the constrained edges, and the original number of edges were 6. So the energetic cost of adding a molecule per tetrahedron can be thought of in terms of the free energy change in enthalpy, which is delta G. And so we just simply write delta G is equal to minus, in terms of changing internal Gibbs free energy. We assume that there is no change in enthalpy, we assume therefore that delta G can be written as minus T delta S, because delta H is 0. If the number of molecules adjacent to non-polar molecule is n, then we can say delta G hydrophobic for n molecules is n into minus T. Remember, this came from above here. Into minus Kb ln 2. That came from here. Yes. Which means that the delta G hydrophobic is equal to n into Kb into ln 2 times T. We also need to account for molecular sizes, and this is taken into account by considering the free energy cost per unit area. The free energy cost per unit area is indeed free energy cost divided by area, which means delta G hydrophobic is equal to the energy cost per unit area multiplied by the area of the molecule. It's kind of a simple arithmetic, right? So the area of the molecule is the effective interface between the hydrophobic or nonpolar molecule and water. And this is effectively saying that the area encountered by a water molecule or coated by a water molecule in the presence of a hydrophobic molecule. That's what A indicates. Therefore, we can write delta G in its full form as N kBT ln2, which we saw here. Yeah. And kBT we combine into one term and divide by area. And this is very exciting because now we can do some sums. We can do some arithmetic to get an idea of how much this energetic cost of adding a molecule into water is actually. In order to do that, we want to make some simplifications. We assume that area is 1 nanometer square. A is equal to 1 nanometer square. And we then ask how many water molecules are likely to interact for a 1 nanometer square area of interface, right? Effective interface area, that's what we call it. So we simplify and we assume that a single water molecule has a circular cross section. It's not unreasonable if we assume a whole molecule to be a sphere. We know it's a molecule found in a tetrahedron, two hydrogens sticking out of a single oxygen. But we can also assume that it is one big sphere with a radius of gyration. So, and many of you are familiar with radii of gyration. So, if we simplify it in this fashion, then the radius of a water molecule is 1.7 angstroms. It's a circle. With pi r square, substituting r in the pi r square equation, we get A is equal to 0.1 nanometer square, which means that if one molecule is 0.1 nanometer square, how many molecules fit into 1 nanometer square? It's evident it's 10. So 10 water molecules correspond to 1 nanometer square cross-sectional area. So now the free energy of hydrophobicity can be arranged and inferred from substitution in equation 1, because we now know N, which is 10, A, which is 1 nanometer square, and kBT is a constant. And so we end up with a term which is, and we can solve ln2, right? And many of you probably know this. This gives us 7 kBT per nanometer square. This is the gamma hydrophobic energy of adding a water adding into water per unit area. Depending on the size of the molecule, however, this is what it indicates, right? Per nanometer square. Depending on how many fold of per nanometer square the area is, or in nanometers, what is the area of a interaction of a molecule, you will have higher or lower values than 7 kBT. This is a separate topic which I want to spend a little bit of time about, which is what is the meaning of kBT? What is the meaning of kBT? We will encounter it again and again, and this will be something that I hope you will find has some almost universal relevance for cellular biophysics. It's one of those kind of numbers that I really want you to remember. For now, I'm going to tell you that at 300 Kelvin, the value of kBT is equal to 4.1 piconewton nanometer. Very unusual unit. Remember this, and we talk about this later. The typical values of adding nonpolar molecules to water are as follows. For oxygen, with a length scale of 0.27 nanometer, diameter of 0.27 nanometer, assuming a circle or a sphere, the area is 0.05 nanometer square, and the energy cost is 1 kBT. Remember, I said it could be lower, right? The energy cost could be lower than 7 kBT. And this is really interesting because it's saying that the energy is very low of adding water. This is kind of oxygen into water. And this is something that you know. You can enrich oxygen in water. You can dissolve oxygen up to a certain concentration in water. And this is what fish and this is what all aquatic organisms live on. Dissolving water in water is also 1 kBT. Octane, on the other hand, which is an carbon 8 molecule alkane, gives you 1.37 nanometer and 3.14 nanometer square, which means 15 kBT. 15 times higher energy than oxygen for dissolving in water. In other words, the hydrophobic energy cost is very high, which is another way of saying that it is somewhat hydrophobic. And as the solubility or as the length of the chain of carbon chains increases in this direction, butanol, pentanol, hexanol, heptanol, and octane, as I said earlier, and these are alcohols, of course, you notice that the solubility of these goes down and down and down. Yeah, this is what this solubility is telling us, meaning to say that the energy cost is so high that they're less and less likely to be dissolved. Um, Ethanol is not on this, but it's somewhere on the higher side. Now, all this is fine as far as organic molecules are concerned. What about biological molecules, right? The most biological molecule we can think of are proteins. And here I have put together the standard amino acid table consisting of a categorization of amino acids into hydrophobic and polar. Hydrophobic meaning those that are apolar and therefore unable to form the kind of hydrogen bonding network, integrate with the hydrogen bonding network, as compared to polar. And you will see that there is almost an equal distribution with slight bias towards polar molecules in terms of side chains of amino acids. This means that we can also think of amino acids in terms of an alphabet of a hydrophobic, hydrophilic. And this is not a very novel idea because this has been proposed to be part of a principle that may govern protein folding. So, from hydrophobicity and water statistical mechanics and entropy terms, suddenly we come back to protein folding, which is the most fundamental mystery at the cellular scale in terms of biophysics. Because, as you know, AlphaFold and all these new machine learning algorithms, while they have been successful at folding by learning the pattern that is existing, we as humans, as a brain, as a principle in terms of equations, still do not have fundamental principles to explain how proteins fold. And this is also sometimes called the Leventhal paradox. And some of you may have come across it in biology. Um, some of you may want to learn more about it. Please refer to biochemistry textbooks. I will not be dealing with it in detail because it's more of a mathematics problem, but there are fascinating combinatorial questions that arise out of it. And so, with this, I'm going to sort of end here and we will continue on the next topic of viscosity and Reynolds numbers.